This is lecture 46, and in the last class we completed the equalization on the receiver side, the decision feedback equalizer. So overall, we have seen equalization on the transmitter side and on the receiver side, and these are the major kind of equalization schemes which we use to compensate channel loss. So now the starting point is that we started the equalization on the receiver side because we had a limited swing constraint on the transmitter side. And the other thing is that you can adapt the equalization coefficient depending on the channel on the receiver side. That is the big important point on the RX side. So what we, just to put it down, we say that the received signal at the output of the receiver is something which we observe. Okay, so let's say this is received signal x of t which we are observing, and depending on the channel loss, depending on the channel loss, this signal can be something. Okay, let me just draw the signal so that I'm just plotting the I diagram for the signal on the receiver side. So this is more or less an ideal signal you can have, but really what you have is you have so this is in time, this is in this place, and then you have okay. So this is the I diagram for the signal on the receiver side, and this is 1 bit period. So this is what your x of t is on the receiver side. And what at the output means you do an equalization here, and at the output what you want ideally is, I will plus plot the ideal one. This is what you want, right? So you have an observable quantity x of t which is coming at the input of the receiver. So let me just mark at the output of the receiver you have, you actually you have an estimated signal. That means just a very clean signal so that you can have with a comparator to decide on what bit it is. And this is the received signal Dn bit. What you were transmitting was the bit sequence plus minus 1, and what you received with the estimated bit. Now you see whatever is in the black is basically the I diagram due to the channel loss which you are seeing at the output of the channel. But what you want is something very clean, very clean signal, so that you can sample the clean signal and decide what bit it is without causing any corruption to the signal receipt. Okay, so now if I ask you that I am having x of t and I want d of n, which is plotted in red as a signal, and I need to change the equalizer coefficients, means there is some block, let me just say some calibration of equalizer coefficient block which comes and basically change equalization coefficient. You have to do that, because if you're not doing it, means that if you're not doing it, your output will not be good at all, because channel loss changes, so will the equalizer coefficients. And I think this you would have seen with the zero forcing of the ISI or a minimizing mean square error in ISI, intersymbol interference. So can you suggest that what should be observed in this black eye diagram, which I have plotted as a received signal, so that we can correct it and get the red one? So you see, there are two things which we are looking for. We are looking that the bit should always cross at a given point. It's a 1 bit period signal, right? And it should have a if you are transmitting plus minus 1 as a bit, NR is a bit, and if all the channel loss is compensated, then at the output of the equalizer, you should always get plus minus 1 only. Okay, so two things you know from an ideal, let me just write it this. An ideal equalization, for ideal equalization, what will you have? Output of equalizer will have only two signal levels. I'm writing in so many words so that you get that if I transmit d of n as plus minus 1, then the estimated signal value should also be only plus minus 1. It's just an amplitude scaling. If I transmit 0.5, I should, after ideal equalization, I get plus minus 0.5. Okay. The next thing is that when I was transmitting the bits, all the bits were equally spaced. So the output equalized signal should have equally spaced transition. Can everyone relate to these two statements, that the transmit signal was plus minus 1 in amplitude and all the transitions were always at a bit period? Whereas what you received something in the black where all the transitions are changing depending on the data pattern. So this is not something which I want. And the other thing is all the amplitude should always be plus minus 1. So now if I ask the question that what should I observe on the received eye diagram to figure out how much am I in error with, can you identify those two quantities? Red is the observed, red is the means ideally required, and black is the observed. So what should we look for? No, eye opening has a very big thing, right? So if I am saying that the red is the final desired one, and the black, whatever you are seeing, the dashed one is what you are receiving. So I need to observe how much am I in error with. Do we know what? No, we do not know what the data pattern is. So that's why I'm saying we only know, or you can say we can only assume that the signal levels which are transmitted are transmitted like NRZ pattern. This is what you will know. Whether it is an NRZ pattern, it's a RZ pattern, it's a PAM4 pattern, whatever it is. You will know this pattern is the same. So if I say this is an RZ pattern, I can say if it is an RZ pattern, it will have only two levels. But when I look at the actual received signal, I see multiple amplitudes in the steady state, right? And the other thing we know, we surely have to determine that what is the data rate. So let's say you know the data rate, but you do not know the actual bits. So if you know the data rate, the transmit part should always be having a transition at an equally spaced interval. It cannot happen that for same bit like transmitting, that one transition is happening at 5 picoseconds. Let's consider this. So if you are transmitting a bit pattern, something kind of this, right? So now if you see 1 0 0 1 0, all these transitions have to be equally spaced. And if these transitions are equally spaced at the transmit side, then the eye diagram should basically have only single equalizer, single intersection point, transition point, right? So that is a property which we know that this should happen. Now, if you are seeing anything other than that, it is actually an error. Okay, and this error we should utilize to calibrate the equalizer coefficients. Got that idea? Pardon? Right. Right, but the thing is that 1010 data pattern will not give you the ISI. So 1010 data pattern is equivalent to a highest frequency of the data rate, and it will already contains harmonics. So forget, right, let's say forget the harmonics, you have only single sinusoidal. For a single sinusoidal at the input of the channel, you will have a single phase and phase and magnitude response. So all the transitions will change. So you will always see a single intersection point if you plot the eye diagram of a single sinusoidal. But that is not the case if this is a random data pattern. The thing what you can do is you can get some guess of the data rate by first only transmitting 1010. So you would say that, okay, this is the highest data rate I can have. I can get my clock frequency through the recovered from the clock data recovery, and then I can start with that frequency. But as soon as you start having a data, as soon as you start having a random data, then all these transition points are going to change. Okay. So at least I think now it should be at least clear that there are two variables which you can observe. The one variable is your error with respect to your desired transition. Okay. So this error is like error in sampled data. This is the magnitude of the voltage level. Okay. The other error which you can observe is the error in the transition point. So ideal, so let's look both of them. So the first one is that you have many different sample values if you observe at the center. But right now just consider that you are sampling the exact value. Okay, so there are many such output levels, but you know that the in a once the system is very much equalized, it should be only one single level, because that is what was ideally transmitted. So anything which I am seeing is an error around it. Okay, and if I can use that error, then I will tune my coefficients that this error gets minimized. And tuning those coefficients based on this error gives rise to your data-based adaptation. Of coefficients. And this thing is independent of, it's a CTLE, it's a discrete time, it's a DFE, whatever it is, it's independent of that. You observe an error, and based on the error, you tune the coefficients so that the error gets minimized. Okay. Then the other one which I have shown you is that I am having multiple transitions, let's say, and I want only one single transition ideally. So let's say if this is the clocking edge, let's plot it with this. If I sample the value of the transition at the one single clock, then if the clock is higher and lower, means if the sampled value is higher or lower, then I can get the transition error. So when I am trying to get the transition error, I am not trying to measure the time. I am trying to measure the voltage. Means I will measure. So I will measure. Let's say if I measure this point on the transition, that means the transition has occurred earlier. If I measure on the lower curve, let me just plot that also. If I measure a point on this, then it means the value is lesser than the desired value. Then that's an error in the transition, positive or negative. Okay, so estimating the transition error and correcting the coefficients leads to you edge based adaptation. Means you can use this information to tune the equalizer coefficients for a perfect for a equalization as such. Okay. So do you think am I neglecting anything while doing this kind of adaptation? So the basic concept you got that you measure either the voltage error or you measure the transition error. Now how am I going to measure the error? What am I going to do with the error? We will come to it later. But anything I left out in doing this? Okay, clock jitter of clock recovery part will take care of it. That is fine. So this is basically, so here I have not talked that, okay, how my clock recovery part is changing the clock phase, right? That will be there, yeah. Means the thermal noise and random noise and those parts I have not right now touched. This is only, you can say, ISI dominant system. Yeah, that will come. How we'll find the error in the sampling. What? Uh-huh. Yeah, so we will try to change we will try to change whatever coefficients we have to reduce the error. And if we find that the changing that particular coefficient is not reducing the final error, then we will undo it. So we will start with the database adaptation. Let me. So the thing which I have left here is whatever I have done in equalizing the coefficients, I did not even mention that, okay, what is the final BER, bit error rate. Okay. I told that, okay, if you can equalize the channel, then if it is only an ISI dominated system, then if you are always sampling at the center of the eye, it's like you have a 0-bit error. But in the presence of noise, thermal noise, clock jitter and all, you look for the recovered bit error rate. And there is another way of adapting the coefficient where when you change the coefficient, you look for what is the bit error rate have you got. So that is called as a minimum BER adaptation. That is one other way of doing it. We'll first look these two, then we'll go to that later. Okay. So we have this database adaptation. So let's look how can we monitor the signal and change it, the coefficients. So you have the received signal. Okay. And let me just go with a very simple one that this is your signal x of t. And right now I am just having a gain factor C naught as an equalizer tag. This is just a gain factor. Okay. And the output of this is C naught. Okay, this is just a gain factor, so you will have as a multiplied. So let's write it here. C naught times x of t, and I clock this at clock edge phi, and I recover the bit. Okay. So ideally, means if I, so this is just deciding the bit. Or you can also say that I want C naught times x of the sampled value, x of n, should be, ideally, this should be equal to the desired level. So let me just call that desired level as d of n. There's a plus minus 1 level which I am using right now. Ideally, this should happen. And if it does not, then what happens? If it does not, then there exists an error with every sample value which is equals to C naught times x of n minus d of n. This is the error. So I can calculate this error plus minus, this is an error. Okay. Now the thing is, I need to change C naught x such that my this error is minimized, right? And you know that my transmit bits are both plus and minus 1. Okay. So for, let me just say, for d of n, let's just see this, d of n equals to plus positive 1, I will have error C naught times x of n minus 1. Whereas for d naught equals to minus 1, I will have error of n C naught x of n plus 1. Okay. So can you tell me what will be the xn in this case, in the first case? Is positive or negative? Just for positive, right? So here C naught x is positive, so error is positive. So let's say if C naught, so ideally what it should be, ideally C naught should be equals to 1 by xn, right? If this error goes to 0. Whereas for the negative case, xn is negative. So the error amplitude is negative. Okay, so let me just tell you the value. Let's say if xn is equals to plus minus 0.8. Okay, for xn equals to 0.8 and c naught equals to 1, in this example you have minus 0.2 error. In this case, for xn equals to minus 0.8, this error is equals to plus 0.2. Okay, the reason why I'm saying this, that you see for the same, for the different polarity of the bits, the error amplitude is different, but the magnitude is the same. If my, and the thing is, I do not know which bit it is, means it can be positive or a negative bit. So I actually measure with both the levels, positive and negative. So if I want to correct for the error, should I look at the amplitude or should I look at the magnitude? Means if I make C naught equals to 1 by 0.8 in this case, the error is 0 for both the positive and the negative bits, right? Yeah, either you basically need both magnitude and sign and then you multiply and do that part, or is there something which, other thing which you can look for? Huh? Yeah, see, looking at the value of x of n will help you to say whether you are in the positive or the negative side. Okay, that is one way that I can always look for the magnitude of the error, which will take the sign into account. If it's like if your xn was, so this is not exactly you take the xn sign into account. This is like for both the positive and the negative bits, the equalizer coefficient will give you the same error. And you, if you look at a magnitude of the error, you can correct for the coefficient. Okay, so this one is, you can say, let me just plot this. So this one will be, so I'm plotting nothing but mod of En with respect to C naught. So it's at the, whatever the convergence point is, it's same on both the cases for the positive or the negative. The other thing is you can always look for, now this is more commonly used, you can look for an error square, which is for the positive or the negative side of the bit, it will give you the same value. Okay, which is error square is C naught, we just say C naught x n minus d hat of n whole square. This is to basically look for the both the positive and the negative bits. So if I look, let me just plot. This is C naught, this is error square. So you have, this is nothing but I can say this is x of n whole square into C naught minus d hat of n by x of n whole square. Okay, so this value is when C naught is so you can always say, depending on your xn and dn values, you can have this. Pardon? Mm-hmm. No, you're saying, let me just get a question. So you're saying if I just go without, like if I go directly with E, if I do not take the account, if I do not take into account the sign of xn, right, then you will be in trouble. If you take the sign of xn into account, then you will be fine. That is, there is no problem with that. But it's more simplification how you can do it. If I am looking for E square, I may not even look for the sign of xn into account. Okay. Or so what I'm saying is, if you're only looking for error, then in order to correct for the error, you have to look for the sign of xn into account. Okay. Whereas if I am looking for E square, you will see that's not the case. You see, this is this. So think about it. If xn was positive, when I'm monitoring E square, if xn was positive, d hat of n will always also be positive. If xn was negative, d hat of n will also be negative. So in this case, the error is square, which is what I am observing, will give me the same value if I am deviate from the positive or the negative level. So I observe the quantity E square itself and I go and change the coefficient. Uh-huh. Pardon? Uh-huh. Yeah, yeah. So we will have two intersection points. So how are we going to change it? We will come. Okay. So that is there. So that's the whole thing. So let's say you observe 2 points here, as is told that I have E square, which I am observing. Right? So how am I going to change my coefficient? Now that will basically bring up to the, so what I do if I am, so look about this. If I am at this node, then I have to change the coefficient in this direction, right? Whereas if I am on this node, I change the coefficient in this direction. Okay. Now, how do you know in which direction you are if you're observing only E square? Huh? Yeah, so there's both the ways. If you try both the sides, you say, okay, this is E square, I will change it. And then you say, okay, this is not the right one. Now you have to figure out that this is not the right one. And then you go for the other. So that's a two-step process. Whereas as he says, if you see the difference between these 2 points is that the slope is different in both the cases at these 2 points. One slope is positive, other slope is negative. Okay. So if I go and if I go and change the equation, let's say C of k plus 1 is equals to, C of k was at the kth instant. Let me just write it like this. C of k plus 1, this will be different. I need to write instant. So C of k plus 1 is equals to C of k minus, I need to have the slope of error square with respect to C into account, right? And then I need to change the value. So I will go and change the value with some factor mu. So mu is the delta which I will change. So now this is equals to C of k minus mu d square is nothing but 2 times E, and you have C of, you have basically x of n, right? So let me now just basically say 2 mu as single mu, so that we have So in this case now, huh? What is? So the thing is, you use some coefficient. So C of k is coefficient or the gain, whatever I'm using here as coefficient or gain at time instant k, ideally. So you are sampling this every time, right? And you sample once, you get an error, and you use the previous coefficient. So if I have an error, I will go in the next time. I will say, okay, I will change this. I will change this coefficient, and then I will change that is ck plus one. For the next instant, the coefficient changes. So again, I will basically measure what's the error, and so sorry, this will not be this. I'm using here n. So let me just make it right. There is only one time index of k and x of k. Okay. So this is a very basic for a very basic equation which will help you to change the coefficient to finally have a mean square error going to zero. Means you say you keep on changing it, and you know this has only one null. It's like a one low minima, global minima here. So you will settle to it. Either you will settle to it or you will oscillate around it. So let's look at that part. So let me. Okay. So let's say you start from this point here, and you are changing by a some mu, so that from here you jump here, and you keep on jumping, and then you may keep on oscillating in between these points, like it is very small. And getting an exact is like you will be always be in some range. Now, how bigger is this jump depends on your mu, xn, and other parts. Okay. Now, if let's say my mu is very large, I can always keep on doing this. But if my mu is very small, I will take n number of steps to come down to the minima. So it exists if mu is very large, you have like coefficient ck may not settle at all, or c may not settle at all. You will always keep on oscillating between the global minimum, between the minima. Whereas if mu is very small, then what can happen? Yeah, it takes a long time for settling. So there is always a trade-off between the two. So the things which are also done is that initially you can have a larger gate, see larger mu, and then you dynamically adapt the mu once you are within the range. But you need that more freedom that to gauge whether you are away, how much away you are. Okay. So this is just you see that by using only one coefficient like a gain block, I can sample that the center of the data, and I can tune the coefficient to have the desired value. Now, in an actual equalizer, what do you have? You have many taps. So let me just say this is your x of n. So I'm just writing in a more like a simplified manner, and you have this x of n minus l minus 1, let's say. So these are all the blocks, and you have gain C0, C1, and C of L minus 1. And all these gains are there, and you sum it up, And this is what you are looking at, the equalized signal. So now this equalized signal y of n is equals to your sum of, sorry, y of n is equals to sum of c of k, x of n minus k, k is 0 to L. This is just an equalized signal. Now I need to measure this sample value or at the data at the sampling instant with respect to your desired point, which let me just say this is equals to, error is equals to y of n minus uh, d of n, which I am right now using as a plus minus 1. Now, no, right? So you see in this particular, x is the received signal. So this is the equalizer which, so this is not specific to DFE or anything. This I am right now still talking of something as you can say as a feed forward equalizer, where the same signal is delayed, right? You will not equalize. So first thing is, do not think this is a DFE. DFE is a different, it will come. This is whatever the signal is coming, you are doing a feed forward equalization on top of that. So the signal itself is delayed. Okay, so then can you relate that this is x of n and x of n minus 1? Is there any confusion in that? No, x of n is the received signal. You are, okay, if you kind of not remember, so you see that I can so this was the signal which I received, right? X of t. And if I want to do any kind of FIR or feed forward equalization on this, what did I do earlier? I had, this is just like I told you, this is like a sampler mode or flip-flop circuits where I sum all this and I sample this. You've seen this equalization, right? So this is just a delayed version. You can do that thing on estimated bits later. Okay, so this one is equals to sum of k equals to 0, L Ck x of n minus k and minus d of n. Okay. Now the thing which I have used just before, the C naught thing, okay, like calculating the slope at whatever I am observing the e square value, I'm going to do the same thing here. So my tuning the coefficients will be C of, okay, so let's say C of m, where m is between 0 to L minus 1. At time instant of n plus 1 is C of m time instant n minus mu e square by d of Cm. I see, so what I do, I have the error value which is due to all the coefficients, not like one single coefficient. But I measure how does the error changes with one coefficient which I want to tune. So this is derivative only with respect to Cm. It's not with respect to all the, for this particular coefficient only with Cm. So this is equals to Cm of n minus mu, same 2 factor here, E of n time x of n minus m. So let me just, is there any problem? Wait a minute. So you look here, right? So this is basically C of, not C, x, yeah, x of n minus m. So let me just write it here. Cm of n plus 1 is Cm of n minus mu e of n x of n minus m. So if you look the figure, the thing which I have just drawn before, you see the C1 coefficient. The C1 coefficient is having a x of n minus 1 as the input. So the equation is taking that into account. The Cm coefficient is having a x of n minus m as the input. So for all the so you will see that with respect to each of the coefficient, it is a quadratic in nature. So for all the equalizer coefficients, it has a local minima. Each equalizer coefficient has a local minima with it, and with that we will find a global minima for the equalized value. And this mu is the parameter by which you change. Okay. So is this clear? Any questions on this? Because then we will. No, this here you do not need the sign of the error. So this is also called as full least mean square algorithm for adaptation. You are taking the mean square you are taking the square of the error, and you are using the square of the error to tune these coefficients. And you know this x of n is it will turn out to be a random variable. Plus, it can be positive and negative both the case. So in a mean square sense, you are optimizing the coefficient. Yeah. What about the thermal noise or something? Right. Okay, so the thing is, this is adaptation of equalizer coefficient on the receiver side. Okay, this is right now not considering that, okay, if I do this equalization, it will enhance the noise. If I do DFE also the similar thing will apply. This is easier to understand, I hope, and that's why I'm going with this, because in DFE coefficient, it will be a slightly different case, but the algorithm is the same, that you measure the error with respect to the amplitude, you change the coefficients to reduce the error. Okay, the same thing can be done for the DFE also. We can look at that DFE part. That's not anything. And this is also, you can say, it's not only for a feed-forward equalizer. Let's say I am doing a continuous time linear equalizer. I am equalizing the signal, and there's the C is not a gain as such block. Let's say you are tuning the resistance in the equalizer for the channel loss, right? So I observe the value, what is the final value, and I go and tweak the resistor. So this will apply in all the cases. It's a very general way of tuning the coefficient. Yeah. Now the question is, how do we measure the error signal? So let us see. So what is the error signal? The error signal is this one, right? The blue, the one which is marked in blue. That is the error. Oh, trying to get it with the same color. So the error signal with respect to the desired, let's say this is the desired Y. Let me just write it as this is the desired level, D level. So if I want to measure the error signal, what shall I do? I know D level what it should be. I mean, the way I have shown you here is if I subtract it, right? If my Dn is a plus minus 1, I know this is the output signal, and that is also the desired signal. I just subtract it. But if I want to subtract it, either you go with the brute force subtraction, or what's the easiest way can you think about? Huh? Okay, you can do the current source way. That is little more difficult for me. So I will go for the easier way out. Huh? So, okay. one thing is you are having an x of n, right? For x of n, I can always, so let me show you a couple of ways. So I have an x of n going here, I digitize it and I get a certain value. Let's say some n, and I'm using many times, let's say some p levels or p bit, whatever, and then I compare with the dlef. That is the one way of doing it, right? The other way is if I use x, so let me just give you a more simplest way, is if dlef is a threshold for the comparator and x of n is the input which you compare, and the output gives you only +1 or -1, what kind of quantization have I done here? So earlier you were seeing that the error can have a magnitude. Now what I have done is I have quantized that error only to high or low as compared to my dlef, right? Did you get this part? So in order to measure error, so let me just again plot it here. So I have many of these xn here, and I have the desired signal this. My error can span anywhere between this and this in a real sense. But I only said that, okay, my error is either this or this by doing this comparison. So I have only basically got, ideally you can say, the sign of the error, more practically, sorry. So by doing this, what I got the sign of the error, E of n, right? So in place of using the whole error value, I have only the sign of the error. Right? Now I also need to get x of n minus 1. How can I get the, so this is like, if I do not do anything, I have to get two analog quantities and multiply them. This makes one. Both are analog, and I have to do multiplication, which is a hard part to do in analog, not that easy. If you want to do in digital, you need to first get a certain bit resolution and then you multiply in digital. And you think about it, if I am going to do all this thing within the every next cycle, which I am going to tune my coefficient, how difficult it will be to do in the digital block at a data rate of even a gigabit per second. Right? So the easiest way is you do a very coarse quantization on this and you get only the sign of the error. That will basically make you to come closer to the final settled value, but it will be with coarse amount. So the way I have used my sign of error of n, I will also do the same thing for x of n minus 1. So I will also get the sign of x rather than the actual ideal value. So n minus mu times sign of n, sorry, en, and sign of x of n minus 1. And this thing is called as sign LMS adaptation. Okay. So this is like much more commonly used LMS adaptation for the equalizer coefficients because it's the most simple one. The problem with doing this thing is that now if you are using the same mu or update value, mu is an update value every time instant. If you use the same update value, now you will be making a bigger jumps. So you cannot use that large mu value anymore. You have to change the mu value to a smaller amount, and now that is going to increase your convergence time. So that is a drawback, but this is much faster to calculate all the product and everything. Okay. So, and all these things have a, like they will settle to a final value. They have some other global minima. Yeah. For a given. Uh-huh. Right. No, in a mean sense, it will converge, right? So when, no, let me just, yeah, it will keep on fluctuating. Yeah. So the thing is, okay, let me tell you this, then let me see if you have still a question. So, and let me just draw this. So the thing is, you start from a higher value, right? And when you come to a very close, you may keep on fluctuating. So the E of n, so you are basically having a very small mean square value. It doesn't say that you are forcing E to 0. That is not at all enforced in this case. What is enforced is that the mean square, that E square, is very small value, and the settlement is in that case. So you will start, let's say you start with some coefficient, you can plot it. So let's say you start with a very high value. No, this is I'm plotting with respect to time. So I start with a very high value of C of n, and I will keep, and let's say this is the ideal value for it to converge is this. Okay, the way it will converge, it will start from here, it will come down, and it may basically, it will means if I just exaggerate it, it might be doing something kind of this. Okay, so it has settled in a mean square, in a mean sense, it has settled to the final value, but it has not basically settled to the exact value where it doesn't change at all. Okay. Mm-hmm. At the top point, yeah. Sign of, if sign of En changes, Xn will also change. Mm-hmm. Mm-hmm. Yeah. Okay. Means you mean to say it can also go up? This one. So here it can also come from here, no? So the, if you see, right, the way we started was, I think this is what you might have. So we started was this, no? You can start from both the points on the right or on the left. That is equiprobable. Let's say that's the starting point, right? But when you start there, you are always coming down to the place where you're minimizing the error. Hmm. Okay, so let me just take an example and see. So I think, what's the time right now? 56, right? Okay, so let me stop here and take it on the board. Okay, stop here.